Okay, welcome to Activity 21, Polymer Parts. We're going to walk through this together and make sure you have your notebook set up, your online notebook set up for Activity 21. Make sure you get the learning targets down as well and our challenge. So here we go. Can you imagine a world without plastics? Plastic soft drink containers, bags, pens, DVDs, and computer and television parts are just a few things made of plastics that would be different. For thousands of years, however, people lived without plastics. But today, materials scientists and engineers have created plastics to make everyday products. In the past were made from glass, metal, and wood. In this activity, you will read how a plastic, a synthetic polymer, is made through a chemical reaction. So our challenge is, what is the chemical structure of plastics? And on the bottom here it says, Bakelite was the first synthetic plastic invented by a Belgian scientist named Leo Baekeland in 1907. So in the 1920s, the versatile Bakelite was manufactured to make all sorts of products from auditorium walls to radios. Okay, our materials. Let's double check with Mrs. Cook or Mr. Brookins to make sure if we need these student sheets, 21.1 and 19.1. If we do, make sure you have those ready as we read. Plastics are polymers. What makes plastics different from other materials such as glass and aluminum? The answer is found in the wide variety of plastics and compounds that can be made from chains of carbon atoms. Scientists make new plastics by designing compounds with a wide variety of properties. The majority of plastics used to make products are synthetic. This means that they are made in laboratories and factories and do not exist in nature. The first plastic was developed in 1907. Some natural polymers include the cellulose that makes up wood and cotton, the protein that forms strands of human hair, and raw rubber that is collected from rubber trees. Plastics are part of a larger category of compounds called polymers. A polymer is a substance made up of thousands of repeating small molecules. The prefix poly means many, and the word polymer means many parts. The small molecules that repeat in a polymer are called monomers. The prefix mono means one, and so a monomer is one part. You model the formation of a polymer made from many tongue twisters, monomers when you attached paper clips to make a long chain. Each paper clip represented the monomers that bond together to form a polymer. The long chain of paper clips represented the polymer. Say that one 10 times. To take polyethylene, for example, that the plastic that was color-coded red in Activity 18, Properties of Plastic, was polyethylene. Polyethylene means many ethylenes, and it is a chain of ethylene molecules. The ethylene molecule is a monomer. Okay, take a look at that diagram. We have ethylene, which is a single molecule, and it's a monomer. And over here we have a polyethylene, which has thousands of the same molecule linked together, and it is a polymer. Continuing on reading. Adding the prefix poly to the name of a monomer forms the name of many synthetic polymers. Think about the other plastics you use in Activity 18. Polystyrene, a chain of styrene molecules. Polyvinyl chloride is a chain of vinyl chloride molecules, high density polyethylene, and a chemically bonded chain of ethylene molecules. And polypropylene, a chain of propylene molecules. I'm probably really messing up these words, so I really apologize. Continuing on, synthetic plastics, like the four you invented in Activity 18, have been in use for less than 100 years. However, people have been using natural polymers like wood, natural rubber, and wood for centuries. And continuing. Investigating the structure of polymers. Scientists began to investigate the atomic and molecule structure of natural polymers so that they could learn how to make synthetic polymers. In 1920, the German scientist Hermann Staudinger proposed that polymers were made of long chains of many small molecules. He thought that the length of the chain was related to the physical properties of the polymer. At the time, his ideas were considered radical, and many scientists did not take them seriously. But he continued to collect data, and that supports his ideas. From his work and the work from other scientists, dozens of synthetic plastics were developed. Staudlinger's research on the properties and structure of plastics was so important that he received the Nobel Prize in 1953. Today, scientists know that changing the length of a polymer chain is not the only way to change its properties. Another way is to cross-link a polymer. You model this process in Activity 19, Designing New Materials. When you mix the polyvinyl alcohol with sodium borate, the sodium borate provided the cross-links. You also modeled cross-linking in Activity 20, Modeling Polymers, when you cross-linked paperclip chains with a different colored paperclips. Think about how the properties of the polyvinyl alcohol and the sodium borate were different from the properties of the cross-linked polymer. Okay, so we have polyvinyl alcohol plus the sodium borate, which is reactants, cross-linked polyvinyl alcohol, and it ended up being the product. Why does cross-linking a polymer change its properties? New chemical bonds form and change the structure of molecules. The polyvinyl alcohol and sodium borate are reactants, and the result of their chemical reaction leads to the formation of a new product. The molecules and the physical properties of the product are different than either of the reactants. As Staudlinger found, the number of cross-links is related to the physical properties of a cross-linked polymer, just as the length of the polymer chain was related to the physical properties of the polymer. If there are a few cross-links, the cross-linked polymer has a memory. After it is stretched, it remembers to return to its original shape, much like a rubber band. If a plastic has more cross-links, the result is a harder substance that cannot be stretched and does not return to its original shape. One problem with cross-linking that is often difficult to reverse. In fact, the more cross-links there are in a polymer, the harder it is to break down the polymer chemically. This means that the cross-linked polymers are usually difficult to recycle. A polymer that is commonly cross-linked to improve its uses is rubber. Natural rubber gets sticky in hot weather and brittle in cold weather, and it falls apart very easily. When the rubber is cross-linked, its properties change. Cross-linking rubber makes it more stable and elastic. Most of the rubber products in the world around you, from food containers to car tires, are made of cross-linked rubber. While this makes better products, a trade-off is that it causes disposal problems. Cross-linked rubber is also stable, that is not able to degrade. This can make recycling cross-linked polymers difficult. However, there are ways to reuse the material. For example, the old tires can be shredded to made into chips. These chips are used on playgrounds, running tracks, and in road construction. Scientists and engineers have developed ways to use old tires as a source of energy. So it's estimated that 2 to 3 billion tires sit in landfills across the United States. This is an environmental disaster or an opportunity to find new ways to deal with them. Okay, for your analysis questions, make sure you double check with your teachers to see which one you need to do for homework. And thank you for listening.